Hi, everyone. So we're going to look at weight maps and dig a little bit deeper into why it is hard to make local inference about them, and is there anything we can say about them? So just as a quick reminder, linear predictive models are parameterized by a weight vector and a bias. It can be seen as a hyperplane. The weight vector is used to make predictions on new examples, and it is estimated by solving an optimization problem that consists of a data fit term and a regularization term. And W has the same dimensionality as the input data. So in our case, we can plot it as a brain image if we take a brain image as input. So many studies, if you look at the papers doing MVPA, interpret those maps to varying levels. That means they can say, well, this feature contributes to my model, but sometimes they say, well, the sign of the decision function in that voxel is positive, which means that the signal in that voxel is highly predictive for class A. So what do I mean when I say, can we interpret the weight maps? So if we look at the machine learning community, typically a model that can be interpreted means that it identifies a subset of contributing features. Now, in neuroscience, typically, we also want to know why these features contribute to our model. And different techniques can find a subset of contributing features, but there is evidence that knowing why these features contribute is actually not straightforward. And if we take Schrouff et al. In 2014, they mentioned that classifier weights can exhibit small amplitudes for measurements that contain the signal of interest, but also large amplitudes for measurements that do not contain the signal of interest. So that's kind of a problem. So let's first look at, it's a multivariate map. And we mentioned we can't make local inference, so why is that? If we take our predictive function, when we have a weight map, let's say here we have 4 features. We have the weights for those 4 features that we obtained by training our model, and we have a new example, X star. Now we make the prediction for that new example by multiplying the weights by the new example. And we obtain a prediction which is f of x equals 1. And that's the predicted score for regression or the distance to the decision boundary for classification. So here, let's say it's going to be class plus 1. If you actually look at the weight map, it's the weight map for the Haxby first subject, houses versus faces. So in this case, it would be actually predicted as a face. Now, I want to make local inference. So I'm going to look at those weights that have the largest amplitudes. And I'm just going to, basically ignore the others. So it's like they were set to 0. The problem with that is it actually gives you another predictive model. So if you look at that model and you multiply it by that same example, it gives you a different prediction. It gives you now -2. And that would be actually the other class. So it would be houses in that case. So basically, when you threshold the map, when you just look at those highest weights, you are looking at a model that you have not estimated. You do not know its prediction accuracy. So in this case, we can see that f of x star does not correspond, the truncated version or thresholded version does not correspond to the predictive model. So I also mentioned that the weight amplitude could not necessarily represent the signal. There are different factors that can influence that. So I'll spend some time over this and explaining the problem rather than showing solutions. But maybe other people will touch on that later on. Maybe Bertrand will. So in Hoff et al., there's that small example. So you have two data channels. One contains signal of interest that is correlated with the two classes, for example, C1 and C2 that you present. And you have random noise. So on channel 1, you have the mixture of signal and noise. And on channel 2, you have only noise. So what can the best classifier do? Well, it will simply say that give a weight of 1 to channel 1 and of -1 to channel 2, so to get rid of noise. So if you look at the magnitude of those weights, well, they are the same. So basically, you are looking at those weights, and you're like, for you, channel 1 and channel 2, they have the same importance. But you see that in terms of, like, let's say, input signal, it just does not represent the input signal correctly. And there is a mention in that paper and in others on whether this actually depends on the signal-to-noise ratio. So I actually quantified this using simulated data. So there was a simulation of conditions A and B. I said A is signal, so I added signal on trials from condition A and not on trials from condition B. And I kept the correlation structure from breast data. And then I varied the signal-to-noise ratio. And I compared the weight maps with the discrimination A minus B of the input signal. And if you look at this for an SNR equals 3, then you have, so basically the blue line is the effective signal and noise you obtain in the simulation. So it's A minus B. The orange line is the weights of an SVM classifier that discriminates A from B. And then the gray line is the input neuronal signal, so without the noise. And we actually see that the weights are not doing too bad. And when you increase the signal-to-noise ratio, it does better and better. So yes, this depends on your signal-to-noise ratio. Then another effect is not only the amplitude of your signal compared to noise, but it's also the structure of that noise. And so when you have covariance between the variables, so let's say you have two means, one blue and one orange, sorry. They represent different classes, and you see they have different values along the x-axis, so you could discriminate them by putting a line that depends only on that x-axis. Now, if you add covariance to those data points, you obtain samples that are distributed according to that covariance, and they can still be discriminated, but that decision function does not represent where your signal difference is, because in this case, it will use both features to give you significant accuracy or the best discrimination, while actually if you just look at the signal means, you see that you only should use one feature, the x-axis, to discriminate between your classes. And there is another case, which is that the noise covariance can depend on the classes. So in that case, the 2 points, they have no main difference, but they have different covariance structure, and these covariance structures depend on the classes. So I actually don't completely agree with the example of that paper, because if you look at the total or balanced accuracy, it will give you a number that is around 60%. But if you look at the class accuracies, you have for the blue class, it's 100%, and for the orange class, it's more like 25-30%. So this is a model that I personally would not consider as significant or performing well. I think Bertrand will touch more on that. But basically what they want to say is that in that case, even just the fact that you can have differences and dependencies of your noise covariance can give you significant discrimination, while actually there is no difference in your signal mean. So what influences the weight amplitude? So as we've seen, an association, so a high amplitude can be related to an association between the voxel signals and the labels, but also due to multivariate properties, which is correlated signal or correlated noise. However, that is mitigated by high signal-to-noise ratio, or also by high intrinsic dimensionality. And the word intrinsic here is actually important, because when you deal with fMRI or with other type of neuroimaging data, the dimensionality of your data, which what they refer to as the number of independent variables, is much lower than the number of voxels or number of variables you record. And on the opposite, a zero coefficient can be due to no association between the voxel signal and the labels, but also due to a particular type of regularization. So basically, if the goal is to make local inference about the association between the underlying brain signal in a voxel and the labels, then just do not use MPPA. We say further analysis. I mean, you can do different things, but basically, machine learning is just not made to answer that question. Okay, I used my model because I wanted to predict things, and I still have a weight map. Should I just not use it? Well, not really. It's just you can't make local inference. So it is a spatial representation of the predictive function. It's always a good check to actually look at it, because sometimes it just as a sanity check to see if you know basically where more or less in the brain your information should be. It's a good sanity check to make sure that you don't have high weights, for example, around the brain, where you could, oops, sorry. No, yeah, no. I don't see it. Okay. So if you have voxel, like high weights around your brains, then maybe you're just classifying movement. And it just gives you a good idea of what's going on in the model. It is a multivariate pattern, so no thresholding. And it is a mixture of signal of interest and of noise, but the extent to that, it's still basically being investigated, because it's going to depend on a lot of factors. So I mentioned earlier that there were strategies that could help to identify a subset of relevant features, which is basically the only thing we can really do to help with model interpretation. I listed 9. It's not an exhaustive list, and I do not have time to go over all of them. But basically, there are 3 levels that you can do that. There's a priori, so you can select a region of interest, or you can apply searchlight mapping. Janina mentioned it. I will go into more details. Then there is during the model estimation, so you can do feature selection, and or you use regularization with especially sparse algorithms. So these are specific types of regularization that enforce sparsity. We have atlas-based multiple kernel learning. It should actually be a subcase of number 4. And we also sometimes do weight stability during the model selection. So basically looking at the reproducibility of the weight maps across folds, and including that in the optimization function. But it's still, the weighting, for example, between the two is still kind of a debate. Then you can look at things a posteriori, so you can summarize your weights, just do regional averages based on atlases. You can do permutation tests, so you run permutations, compute the weights for each of those permutations. And then you threshold the weight map based on the significance of the weights in each of the voxels. And you can also transform the weights into an activation pattern. That's actually another model that you would apply to your weight map. So I will just go a little bit more into searchlight and sparse models, and especially the atlas-based MKL that we just have more experience with. So for searchlight, you scan the image volume with what is basically a neighborhood. So you pick a voxel, and then you select a neighborhood size. So in this case, it is like neighborhood of size 1. And so you end up with 7 voxels, and you apply your classification or regression to just those 7. You obtain an accuracy. Then you slide 1 voxel, and you do it again. So this is really a mapping approach, and it is local. The good thing about it is that you obtain an accuracy for each of the voxels, and you can compute significance for each of those neighborhoods, and you can threshold your map. It is locally multivariate, so it does not account for the whole brain network. Like the choice of that neighborhood size is basically a parameter, and you have to decide that a priori. You build as many models that basically they are voxels. So it is a lot of comparisons that you're performing. So you need to correct for that. It is not as bad as with univariate techniques, but and there are analytical approach to that, but it just needs to be performed with care, and you need to like look into it before you do that. And it is very computationally expensive, especially if you run all the permutations. So let's look at sparse algorithms. So these are special types of regularization. There are many different types. Lasso, elastic net, total variation. And if we actually, Janina showed that figure before, actually. So it's for the same accuracy, for the same level accuracy, this basically, the regularization is basically a hypothesis you make. And it's going to affect like a huge amount of the weight map you obtain. So it is embedded in the model, which is good. It's data-driven, and it identifies a subset of predicted voxels. But you can have quite a lot of instability of the selected features based on the regularization you select, but also across folds. And so as a basically sub-method of that, there is atlas-based MKL. So in this case, so Janina mentions a little bit about the math behind MKL. So here we'll go on an application to try and improve interpretability. So here the brain images are segmented according to an atlas before we compute the kernels. So if we use the AAL, there are 116 regions in that atlas, and we obtain 116 kernels. And then during multiple kernel learning, for each of those kernels, you have a decision function. And basically, the final decision function is a weighted sum of those kernel functions. And the weight, so basically the contribution of each kernel, is sparse in this algorithm we are using. So some regions will be entirely pushed to 0, and some regions will contribute to your model. So it does give you a list of regions that contribute to your model. It's a very sparse list because it's an L1 regularization on the kernel contribution. It is a list that comprises regions that do make sense according to an anatomical or functional atlas. You do choose that atlas, so it is, again, a hypothesis. It does not, it's an L1, so it does not select correlated information. So if you actually apply that to the Haxby dataset, if we go there, you see that you have the fusiform region that is picked on top from the left side quite consistently, but the region from the right side is actually a bit further down. So because in some folds it is picked, and in other folds it is pushed to 0 because it has correlated information with the fusiform left. So you do obtain with that method quite a few false negatives. Another example of that is with intracranial EEG data, which in my experience is much sparser than MRI, fMRI data. So here, the subject was looking at different types of images and resting, and we compare each image versus rest. And so we have face versus rest, and if you look at the signal, so you have one channel that is picked, and it has a really high z-score for faces compared to everything else. Now, if you do at buildings versus rest, the channel right next to it is picked, and that signal has a really high z-score for buildings compared to the rest. So we see that here it's very apparent that the model identifies only that channel. It does not try to take out some noise from it, just because the signal-to-noise ratio is quite good, and the data is relatively sparse by default. Now, if we take the animal versus rest, we see that that classification is a bit less easy. It's a bit more noisy. The scale is actually smaller, which is not reflected in that plot. So it does go and pick more channels to try and eliminate that noise. So in summary, interpretation of machine learning-based models can be complex. The weight and amplitude can depend on multiple sources of variations, not only on the means differences between the signals of interest. There are different strategies to select a subset of contributing features. Each one has advantages and limitations. As I mentioned, I didn't go over all of them, but we can think of whether you want something that is data-driven or that is based on an atlas or a priori knowledge, like selection of a region of interest, what multivariate power you want, if you want something local or more global, the stability of the patterns, and computational time is getting less and less of a concern, but it is still definitely like something you want to keep in mind still for the moment. And so basically machine learning models were not designed to answer why a feature is important. So the best we can do is to try and select a subset of features contributing to our model, but really answering why that feature is important is and will remain quite tricky. So it can be used, your weight map can be used as a check that your model actually relies on neural activation. And if this is really your goal, then I would suggest to use another method simply. You can also do multiple analysis of your data, univariate and multivariate, and compare and just make sure everything is looking good. Quite a few things that I presented, I created with Pronto that Janina mentioned before. So this is the poster number, and we have a demo on Wednesday. We do have a talk tomorrow at 2 in the open science room as well. And then on the website there, you can download, and it's quite documented as well. So I want to thank Janina and Christoph and people from the different teams, especially at UCL, but also at Stanford, who provided the intracranial EEG data.